Alright guys, welcome to Open Source Options. Today I'm going to talk to you about how all maps lie, and I'm going to do it using an orange. So let's get started. Our first task is to take this orange, tangerine, halo, whatever you call these things, and we're going to have to cut it. Now the reason I'm using this is because it's roughly a sphere, which the Earth's shape is also roughly a sphere, though it's not quite. You can see that I've attempted to draw the continents on this tangerine, and as you can also tell, I'm not the greatest artist. But I'm going to cut this in half and try and pull these halves off so they're still rounded, so I can show you the reason that all maps lie. Let's go ahead and give it a shot. Okay, we'll try to keep Africa intact. So I think it's going to give us the best example for how to do this. So let's pop the top off. Let's make an incision to get this across half. I'll try to do this without making a huge mess on my desk. And I'll speed this video up so you don't have to watch this entire slow process. There we go. There we have half of the Earth, and it's still curved. Now I'm going to show you why maps are all incorrect, and we'll explain the principles of it on the whiteboard after we do this. You can see we have a curved surface here. All the maps we view are flat. How do we represent this curved surface on a flat surface? Well, the answer is we have to smash it somehow. Somehow we have to get it to fit our flat world, to fit our paper maps. And so we're going to smash it. And if we do this, you can see that we make indentations. And we can flip it inside out, but it still doesn't really fit. The only way to get this curved surface onto a flat surface is, as you can see, to make a little tear. And as we tear this, we can now warp it to become flat. You can see that as we've done that, we've torn the camera over. We've torn a part of Africa here. We've torn through Europe here in order to make this lay flat. And this principle, putting a round object into a 3D object, 3D round object, into flat space, is why all maps are wrong. And let me demonstrate this on the whiteboard now. So let's take a look at why it is that we have such trouble graphing or displaying or representing objects from a sphere or spheroid like our Earth on a flat surface. Now, first, let me show you how we generally describe things in mathematics spatially. We basically have a two-dimensional grid, like this. We have our x's down here. We have our y's over here. And then we can plot things. We can plot a line, which is just a function. We could plot a different kind of function. Maybe something looks like this. We could even plot something like a polygon, which is spatial, like a country. We can plot points like this, which are spatial data as well. And we can plot things like, let's say we wanted to plot the state of Utah, because it's easy to draw. It would look like this, potentially in graphical space, where we just have our x coordinates here, and we have 1, 2, 3, 4, 5, and Utah goes from 3 to 5, 3 to 4 up here, right? So we could plot those things out. But the reason this doesn't work well with the spheroid, I'm going to show you two reasons why this is. So let's get rid of this layer, and let's pick a new one. Now, the first reason, we have to just show you how the globe is broken up. Because it's round, we use angular degrees, okay? Which means we're not going to get straight lines in some cases. But let's go ahead and start doing this. So we have latitude and longitude on the globe. Our latitudes are our y coordinates. Our longitudes are the x coordinates. So let's start with the line of latitude, roughly the equator. Looks something like that. We can go up and make some more lines of latitude. We'll try to make these equally spaced, though I may not do a great job of it. Okay, and then we can go down in the southern hemisphere and make some lines of latitude, just like this. Try to mirror the ones in the northern hemisphere. And you notice that these are parallel, which is great. So if we came over and we put these lines of latitude on a graph, they're going to be y coordinates. And I'll try to do this as easily or as cleanly as possible for you. But if we draw a graph over here, oh, that's not going to do good. Let's try to make that straighter. If we draw a graph over here, that's pretty good there. And we draw these corresponding lines of latitude. So we'll come across here and we'll try to draw these straight across, come across here. So they correspond to the lines on the Earth that we've represented here. This is roughly how we make a Mercator grid, which is probably your most common map projection. Okay, like this. And this would extend up just a little farther, something like that. Let's get rid of that last line and try... Well, it looks like that. Okay, so there are our y coordinates. So these are y coordinates, and those equal latitude. Okay, that means our x coordinates, if my pen would work, equal longitude. So x equal longitude. Now here's where we should run into the problem. So let's draw some lines of longitude. Now if you've seen a map before, you know the lines of longitude converge at the poles. So if we put a dot here to represent each of our poles, and we draw our lines of longitude, we can see that they curve. And these aren't going to be exactly right, but we'll try to get them close. And we might have to draw one in there to even things out just a little. Okay, and so that's how we divide our world up, our globe up into a grid. Now we have 1, 2, 3, 4, 5, 6 lines here. So if we divide this roughly into 6 equal portions, it's going to look something like this. 3, 4, 5. Oh, that one got a little bit close. Let's undo. Let's get rid of those last two. Maybe. There we go. It's 4, 5, 6. So that's roughly how it would look if we divided this up into a globe. Now, let me show you where we run into problems. Let's zoom back in here. So if we take a look at the spacing, our x spacing, somewhere around the equator, so somewhere in one of these two grid cells here. Look at this distance. The distance there. Let's use a different color actually. Let's use red. So the distance here and the distance here are not the same. As you can see, the northern distance is much, much shorter. Now I've tried to space these out nearly equally. I don't know how good of a job I've done, but we can try to demonstrate this by drawing Greenland in the same location on this Cartesian grid, this equally spaced grid over here. And if we do that, what we're going to see is that it's going to appear much bigger on this map. Because here, if we took the distances here, our distance across the middle is about the same, but our distance across the top is now much larger. So we're 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So we're over here, and you can see that Greenland covers about half of this pixel and a little bit of that pixel. And it kind of comes down and covers the corner of that pixel and a corner of this one. And it comes up and covers an area of that. So you can roughly see where Greenland is there. And if you look at these two, now I haven't done this exactly right, but Greenland here is actually quite a bit larger than Greenland there on the globe. And that's because we've expanded that pixel size. So that's one way these maps lie, is they distort things at the northern latitudes. Okay, now let's go take a look at one more thing. And that's the other reason that all maps lie. Because there are ways to represent spheres in 3D. We can do that. Now, the reason, and I guess I should say the reason that we can't always represent things in 3D is because there are ways in which we acquire data that do not represent things in this method. So think about aerial imagery. Aerial imagery is just a grid like this. And what you might get in these grids is you're going to get things of different colors. So if we talk about a satellite image, it's taking a photo. That photo is made up of pixels. Those pixels are squares, right? Just like this grid I've drawn over here. We can't partition things out between grid cells like we can with vector data. So this is a vector polygon, and we can represent that in different ways. But with a pixel, we're stuck to representing things on that pixel. So if I'm looking at like aerial imagery, I'm going to have a pixel, and that pixel is going to have one color for each band. So we might have this color that shows up in this pixel. And then we might have this color that shows up in an adjacent pixel, like this. And maybe it has the same or relatively similar color over here. And maybe we get this same color in this pixel over here. And maybe these pixels kind of fade out to different colors as we move along. And this is how we see what's happening in the environment. If you zoomed in on a photo, it would look something similar to this if you could see the individual pixels. Now, how do those pixels get mapped onto a spheroid, right? We have to distort those pixels somehow to map them onto a spheroid. And when we do that, if that image, let's say the image that we've taken, just represents a small portion of one of these. Let's say that the image that we've taken just represents like this little square right over here. Okay, and we have these pixels and they represent this area. Well, now we take another image right here, and we take another image right here, and now we try to convert those and make them into a mosaic where we have points in the north and points in the south. Those points in the north are going to get distorted if we apply them to a spheroid. Okay, so that's just the way that this is going to work. The second reason it doesn't work, and let's see if I can find a little space up here and zoom in to show you. That's going to be really big, but we're going to try it. Is that Earth is not even a perfect spheroid. A spheroid represents a smooth surface, something like this, right? Let's say that's the Earth's surface. But we all know that Earth has mountains, it has valleys, it has oceans. And so Earth's surface looks something more like this if we're looking at the sphere, right? It has low spots, it has high spots. Now this is a really bad representation, but you get the idea. Mathematically, we can't account for all that variation. We have models of the Earth's surface called geoids that account for some of this, but even then, it's more of a smooth approximation. So I'll show you something. So it might look something more like this. If we approximated this, it might be, okay, we've got some low spots there. Generally, we follow the pattern, but we don't quite always get it. And so it's not a perfect sphere, but it's a geoid. And so that's the other reason why maps are going to lie. So all this is to explain to you why we need projections. We have to have ways to represent a 3D spherical surface on a flat piece of paper or on a flat screen. And the reason we need that is because our images are flat. they're two-dimensional, and we have to be able to represent the way that we capture data on the Earth. And so that's why we have projections.